8.4, common and natural logs. We've already dealt with those common logs from that last section. That's just what you saw, is just showing log like this. If it doesn't show the base like that, it is considered a common log. We'll talk more about natural logs in the lesson though. E, the letter E, is kind of like pi. It's an irrational number, meaning the decimal goes on forever and ever and ever, but never repeats or terminates. It is called Eulers Constant. If you want to look up who Euler was and look up all the nerdy math history about him, you're welcome to do that. I'm not going to at this point.
I'll report.
So common logs, natural logs. Common logs, right here. You can, again, it's just a change in format. So a common log like this, which is the button we've been using on the calculator, it means it's base 10. Common log is base 10. Put that on here, that'd be nice. Common logarithms is base 10. Okay? Now, like we saw on that last slide, we have Euler's constant. Euler's constant occurs quite naturally, which is why, if it happens to be something that is a log with base Euler's constant, E, then we call it a natural logarithm. So natural logarithms are base E, which is Euler's constant. Now here's what we have these statements, right? So let's start with common logs. You got log of x. This is common log of x, is how that would read, which is really a logarithm with base 10. Okay, now again, this means that the format, if for some reason you wanted to take a common log and change it into a base 10, I'll use a different color. If you wanted to change this into base 10, you could. But if you have log base 10 of x, then you can just change it to the log of x. Natural log, sorry, common log of x. Suck. Now, if for some reason you were like, you know what, I want to take this and change it into exponential mode, you could. You can say, well, I got base 10 to the power of, in this case, we'll make it y, and then it would equal the product x. Okay, so it all, really what we're going to say is it all stems from exponentials, because that's something that we hopefully are a little familiar with. We're more familiar with because we've seen it more in this class and hopefully previous classes. Natural logarithms, so again, it's an ln. I assume that has something to do with Latin, because I think it'd be logarithm natural or something like that. I'm not going to pretend like I know that though. So if you see this ln x, this reads the natural log of x right there. Now, is it always going to be an x? No. It could be the natural log of 8 or something. I don't know. But right now, for this problem, it's just the natural log of x. Again, that just means that really, your base of your logarithm is x. Okay, so again, if you have a natural logarithm, you can change it to a logarithm of base e. But if you have a log of base e, just change it to natural logarithm if you'd like. So this goes back again. We have a base of e right there. So if you wanted to change this into exponential mode, you'd have e to the power of, again, we'll make it y. And then this would equal the product, which in this case is showing, just like with our natural logs there, or common logs, it was x. Okay, so these are interchangeable, and you can go from one extreme to the other. So if you started with something with base 10 to the power of y equals x, you could just change this to log of x. Or if you had e to the power of something equals x, you could say natural log of x equals whatever the y value is, the exponent. Now this goes back to that last lesson. All we're doing is changing the format. We're not actually changing an overall value. All we're doing is changing the way it looks. Which one's prettier for you? I don't know. You have to decide. All right, this one, evaluate. Natural log, this is the natural log of 0.497. Give your answer to 4 decimal places. If for some reason you can do this in your head, much respect to you. But the calculator is how I'm going to do it, okay? So if you look in the top left, it's 3 buttons down from the top left. You're going to see a button, and I'm not being sarcastic at all. The button is ln. That stands for natural log. You're just going to push that button. When you do, it's going to open up a set of parentheses on the calculator. So it looks like this, ln parentheses, right? Well, just type in what it is, 0.497. And then once you type that in, just push enter. I close the parentheses. I don't think you really have to, but on the calculator, again, it's showing 0.497. Close parentheses. I pushed enter, and here's what I got. I got negative 0.699165. There's more. Oh, wait, there's more.
Just want 4 decimal places.
253. Yeah, so I'm showing the whole thing just so hopefully you get kind of the same thing on your calculator. But yeah, we want to the 4th decimal place there, which is the 10,000ths. The 6 there is going to add 1 to the 1 that's already there. So I end up with 0. Because that'd be 2 now, 6992. And this right there, yeah, thank you, it's negative. Negative 0.6992. Boom, we did it. Well, the calculator did it. So, yeah, as long as we can use the calculator, I am happy to do these, and I would enjoy it, which is kind of, that's what makes math nerds kind of weird. But this one's the same idea, but it's a log now. It's a common log. So once again, you're going to find on your calculator the log button, because now it's a common log, right? So it's the common log button. Now when you push that log, like we've seen, it puts that parentheses there for us. We don't actually put that parentheses there. It puts it there for us. So on the calculator, you're going to see this log parentheses. Well, it says it's of 150. So just type in 150 on the calculator to see the 150. I'll close the parentheses for me, so I'm going to push the close parentheses button. It's just the button, one button above 9, and then it'll show this on the calculator. After that, I'll just push enter. Let's see what the calculator gives us here. Log, common log of 150, enter. I get this beautiful decimal, 2.176091259. Well, this one, just like the last one, says, hey, just give us 3 decimal places here. Well, a little bit different. So the 6, right? The place value immediately to the right is 0, so the 6 just stays the same. And we end up with 2.176. That's our final answer. That means the common log of 150 is 2.176 approximately, because we ain't rounded. But this also means that if you did 10 to the power of this, you'd get around 150, because we approximated, right? Okay, now this one says to do it without a calculator. I really want to use the calculator though. I just love them so much.
Can you show us both ways?
Yeah, so right here, let's do it without a calculator first. Now I'm going to make this equal to something just because it's nice to see what the exponent is, right? And in fact, it's a common log here, so I'm going to show my base of 10 right there. Okay, just so I know what, I'm changing this next exponential mode. Let's see what happens when we do, because I can't just put this in the calculator. So my base is 10, and so my exponent is x, and then this would equal the product there, which is the 6th root of 10. Now, I've got this one in exponential mode. This one is in, or notation. Then I've got my root notation there with my 6th root of 10. I'm actually going to take the 6th root of 10 there and make it base 10, but to the exponent, remember that's a 10 to the power of 1, so it's going to be to the power of 1/6. Okay, so this equals 10 to the power of x. So my bases match, right? And that was kind of that's one of our main objectives when we change this into exponential mode or notation. But now that my bases matches, I can just compare the exponent. So x then would equal 1/6. I don't really need any more principles of equality after that. That should be done. So log base, or common log of the 6th root of 10 equals 1/6. Now, if you do this enough times, you'll notice a pattern, and you wouldn't need all this work. But I don't think anyone is going to get that far with this stuff. But you could. Maybe you start noticing stuff. So if I was to put this into the calculator, so it's a common log. So you're just going to push the log button in there in the top left-ish area. It says log. And then it's the 6th root of 10. So I got to type 6. And then I'm going to push second. So I've got to access my root button. Second, and then I'm going to push the exponent button. Okay, so log, crap, pushed the wrong button. Log 6, 6th root, and then you just type in 10, You can close the parentheses if you'd like. And then if you push enter, you get, so yeah, the calculator,
I got a syntax error.
yeah, we got, well, 0.16 repeating. So I don't really want this decimal, so I'm just gonna push the double arrow button. See if I can do that a little better. It's right above enter. Sorry that looks like crap. But when I do, I get 1/6, just like we had. So this one, no calculator, fair enough. But if there is no calculator, then we got to see the base. This is a common log, which means it's base 10. And again, we're not saying what it equals. So what the heck, we'll make it y. Whatever. You can use y, x, z, whatever you want. If you want to use L, that's fine. Just be careful you don't mix that up with a number. So base 10 to the power of y, just changing the format into exponential notation. And then it equals the product there at 1/100th, 0.01. Well, that's pretty nice, but the problem here is that the bases are not the same. So some of you may be able to tell right now what that y is, what that exponent is. Some of you may not. What I'm going to do is I'm going to show that 0.01 as 1/100th. And this is going to help me because the 100 there I can show is 10 to the power of 2. And as a fraction, I can actually just say, well, you know what, I'm going to make it 10. And if I move that to the numerator, then it becomes 10 to the power of -2. So this 10 to the power of -2 equals 10 to the power of y there. And that's nice because now the bases match. So my exponents, I just need to make those equal, then solve, but no need to solve with this one because it's done. Y equals -2. Now again, if you typed in common log 0.01 in the calculator, it would give you -2 as well. Now I hope you guys had as much fun on this one that I did, because, you know, that was a lot of stuff right there, right? But is it hard stuff, right? Like, okay, take 0.01, change it into a fraction. Again, why were we doing that? Well, because I wanted to see this base 10. And it's easier to see base 10s if it's a decimal, just change it into a fraction like this. And then you can see the 100. Again, 1 would be 10 to the power of 0 if you wanted that. But that would be 10 to the power of 0 divided by 10 to the power of 2. And then the exponent 0 minus 2 would still give you that negative exponent of -2. So you end up with the same answer either way. But again, it's kind of fun to go through that stuff, and we can all rejoice together. So here we go. Because we are compelled to, let's change this without a calculator, but a calculator would still show you the same answer. So it's a natural log, so I'm going to change this into a regular logarithm, but that would be base e, because all natural logs are base e. That's an e right there, not theta, if you wanted to know. And that's of e to the power of -3. Now again, it's not showing what it equals, so I'm going to make it equal. You can make it x or y. I'll make it x. What the heck? Okay, so let's change this into exponent mode, or notation. So it's e to the power of x. Yeah, e equals the product there, which is e to the power of -3. Now, the bases match right here, so we're going to change this, or we're going to change the base, I guess, or just matching bases. The exponents is all we're going to compare. X equals -3. Boom, done. So yeah, if you were to type this exact expression into the calculator, it would say -3. Done. All right, so this is e, Eulers Constant to the power of the natural log of square root of 2. Now, right now, I don't really care about the e, Eulers Constant. What I'm really looking at this time is just the natural log of the square root of 2. Okay, let's evaluate this and see what we get. So the natural log, this is just the exponent part of the base e. Again, we'll get to the rest of it here in a second. In fact, maybe I'll do this two ways, but I want to do this first. So the natural log of the square root of 2, again, this would be a log, base e of the square root of 2, and I'll just make it equal, we'll make it equal x again. And again, this would be the exponent of our original Euler's constant there. So that'd be e to the power of x equals the product, the square root of 2. So yeah, doing this, it didn't really help us. because the bases, I can't get the square root of 2 to match a base e on this one, so garbage, scrap that. Instead of going that route with just trying to see if I can figure out a way to work with that exponent, and yeah, trial and error is okay. I got my base e right there, okay, so base e to the power of the natural log of square root of 2. What I'm going to do is I'm going to go back to the top. So let's start with the original expression here. So I'm going to make this equal to x, like this. Okay. Now what I'm going to do is I'm going to change this into a logarithm. Okay, because I got a base e. So this would be, and I'm going to put an extra step in here. Some of you may be able to skip this step. So it'd be log base e of x. And this would equal the natural log, that's the exponent, of the square root of 2. Yeah, this is looking much better already because I have right here, I've got my log base e. What I can do is make that a natural log. So then I would have the natural log base e, natural log of x equals the natural log square root of 2. Okay, well, my logs, I have two natural logs. They're the same logs, right? And so this one, I'm hesitant to change these back into exponential form. What I'd like to do is just say, look, we pretty much ignore the natural logs here, and we just get to say x equals the square root of 2. In my heart, I really want to do more than that. But for now, that's all we got to do. Okay? So to kind of to explain a little bit more on this, we have a natural log, so it's base e of x. Natural log, it's a log base e of the square root of 2. Again, if we can just get these products to be the same thing, then it's the log of the same thing, right? So log, again, replace this x here with the square root of 2. You get the natural log of the square root of 2 equals the natural log of the square root of 2. Boom, you're good. So we've seen this slide before. If we don't like using factoring to solve our logarithms for the exponential value, we can change the base. You can use the change of base property for logarithms. That's very nice. It allows us to use the calculator. In the past for these problems, we were just using common logs. But the truth is, if for some reason you like the natural log button better, use it. Okay, but those are the only two buttons we have on our calculator that we're using. So just choose one to use and use it. I would recommend using it all the time. But this allows us to take a log expression and just type it into the calculator. Use the calculator to estimate this to 4 decimal places, no problem. So let's use a calculator. Again, our calculators, we can't type this in directly. Some of them do. You know, like if you wanted to look for a calculator that would do it, you could find it. I'm not going to though. So I'm just going to use logs. You know what, this one I'll do twice just to show you that it doesn't make any difference. I mean, you're typing it in differently, but it's going to give you the same answer because we are changing the base. So log base 8 of 0.23, 23 hundredths. I'm going to use common logs first. So with the common log, again, you take the common log of the product, which is 0.23. You can put it in parentheses if you'd like, doesn't matter. And then you divide that by, in this case, the common log of the base, which is 8. Okay, now let's see what happens when we put this in the calculator. So log of 0.23 divided by log of 8, common log, and it gives me this decimal, negative 0.706764,745. Now we'll round that, but let's just go back and say, well, maybe you want to use natural log. So the natural log, again, you type the ln button, but it's still the natural log of 0.23, and you can divide that by the natural log of 8. So let's do that. Natural log of 0.23 divided by the natural log of 8. Enter. Yeah, I got exactly the same answer on that, which we should, because these are the same. This change of base property, in this case, we changed the base to 10, which is why it's a common log. In this case, we changed it to an e, the base to an e, Euler's constant. But it's, again, it's the same base that we're using. So that's why we get the same answer here. It did say to round to the nearest fourth decimal place, the nearest 10,000th. So that's a 7 for me. So that's a 6 to its right, which is 5 or more. So I got to add 1 to the 7 there. It's going to become an 8. So I end up with negative 0.7068. And that's what we're going to call it. That's going to say that's good. So we did have a little practice with the Euler's constant, right? So to access Euler's constant, I think some of you guys found this out already, but I'm still going to go over it. To type in e to the power of 4 here, we've got to get Euler's constant. Now, if you look at the calculator, I think you'd find it, but it's going to show kind of above the button as e to the power of x.
54.5.
Well, before that though, so we're going to type in second, and then you're going to type the ln button, and it usually is the ln button because the natural log is base e, and if you look above the button for the calculator we're using, you'll see e to the power of x. Now when you type this in, you'll see e, and then you'll see the cursor is up here at the top. Again, we just got to type in a 4, so just type in 4 and then enter. Let's see what we get. Again, on your calculator, you would see that cursor change to a 4. So we push enter, and my calculator shows 54.59815,003. That's what mine shows. And it did say it around to 4 decimal places. So my 4th decimal place is 1. That's my 10,000ths right there. The place value to the right is a 5. Since that's 5 or more, I have to add 1 to my target place value, which makes this 54.5982. Done. So again, just real quick, putting this into the calculator. Again, you have to access the Euler's constant function of the calculator. So that's the second function of the button natural log. Let's see if I can do a better box than that. Natural log. So when you push natural log, a second natural log, you'll see on your calculator it says E with the box there. Then you just type in negative 4.5. That's a negative button, not a minus button. Then push enter. So on the calculator showing E to the power of negative 4.5, right? Yeah, I got 0.011108997. But yeah, rounding to 4 decimal places puts us at this one right there, the third one there. To the right is a 0, so the 1 is just going to stay the same. And I end up with 0.0111. Done. These ones are great because we just need to put in the calculator. This one, you don't have to push the second button. All you got to do is push the natural log button. Again, it's at the top left-ish. And then type in 6.77. Then push enter. Let's see what we get. 6.77 there. So I got 1.9125011087. But it did say it around to the nearest 4th decimal place. That's a 5 in the 10,000th place value there. To the right is a 0, so the 5 will stay a 5. And I end up with 1.9125. That's it. This problem is only asking us to change the format. We do not need to actually solve this one. In fact, we can't. There's too many variables. So we should end up with a new expression, but it is the same exact expression, just written in a different way. So it's saying to change it into a logarithmic format, and if we can simplify it, then we will. And I'll explain what that means here in a second. So I'm saying that because it's a base e. So if you change this into a logarithm, from your exponential form there, your base is e, so it's log base e. The product is r, so it's log base e of r. And then this would equal the exponent of v. Okay, now again, this is nice, And it's nice to be able to change this into a logarithm with base e, but log base e right there is actually a natural log. So I'm going to make it the natural log of r. I'm using parentheses there just so we understand the difference between the n and the r. And then this equals v. That's a good enough equation for me. All right, again, we got a base e on this one. That's very nice. And again, some students can actually skip this step that I'm going to show. So I'm going to change it to a logarithm, because that's what it's asking us to do. But it's log, our base is e, so our log is base e. The product is showing is 3, so it's log base e of 3. And I'll put that in parentheses. I don't know, I just feel better about it as a math nerd. But this would equal the exponent, which is just an x right there. Now, like we've seen, log base e is actually the natural log, so I'm going to make that the natural log of 3. So I put parentheses around the 3 just so we know it's the natural log of 3. And this equals x. Boom. That right there is, that's a logarithmic form, but also simplified, right? Because this is logarithm right there, but we wouldn't consider it fully simplified until it's a natural log because it's a base e. And if it was base 10, then we would call it a common log instead. So e to the power of 2 equals x. So it's still base e, and that's okay. But again, it is saying, hey, change this into a logarithm, no problem. Log, it's a base e, so I'm going to make it logarithm base e. It's to the power of 2, but it equals x. Our product is x, so it's log base e of x. And it should always equal the exponent, which in this case is 2. So log base e of x equals 2. Again, log base e is a natural log. So it's the natural log of x equals 2. And, well, that's as far as we need to go on this one. We don't need to solve for x on this one, because even if you did, you'd just end up back here, e to the power of 2. You can type that in the calculator, but that just tells you what the product is. It also tells you the x, I guess, for the natural log, but we don't care about that. We just wanted to change this into a logarithmic format. Here we got the natural log of m equals s, and we just want another equation, but in exponential form. So my natural log is actually log base e, that's my natural log. So this would be log base e of m equals s for now. Okay, now again, this is a logarithm. Let's change it into our exponential format because that's what we're going to do next. So my base is e, so I'm going to make it e to the power of s because our natural log, or logs always equal the exponent. And this would equal the product, which is what it's the log of, and in that case it's m. That's it. So let's graph this. Y equals common log of x. Now, before we do that, though, I'm going to change this into exponential mode or format, form, notation, whatever. A common log has a base of 10, and that's important because then I would have 10 to the power of, in this case, y. That would equal the product of x. Okay, so again, this is 10 to the power of y equals x, which is good. But it also means in my table, which is always x's and y's, because that's going to give me ordered pairs, is I'm going to choose y values and then find the corresponding x value. So as usual, it's always nice to start where with the exponent, in this case that's 0. So that'd be 10 to the power of 0 equals x, which really just means x is 1. So we get 1, 0, and we can put that on the graph. That's my x-intercept. 1, 0 there. And then I'll go up, I guess. Okay, so I'll say, let's say let's say the y, rather, is 1. So that'd be 10 to the power of 1 is x, which means that x is just 10. So I have the ordered pair also of 10, 1, which is right here. Now you can see that's already as far as I can take that on the graph to the right. And I'll prove that because if I were by chance to make the y value 2, well, then you'd have 10 to the power of 2 is x, and 10 to the power of 2 is 100. Okay, so it's going to the right very, 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 very fast. But I definitely cannot fit 102 on my graph. So let's go backwards and see what happens there. So if I make y -1, then I would have 10 to the power of -1 equals x, which would just make 1/10 equals x. As a decimal, that's 0.1. So let's see if we can get this on the graph. I got y is -1, x is 0.1. It's getting really close to 0, which is what we would kind of expect, because here this would be 10 to the power of y plus 0. So our asymptote again is at 0 for in this case the y. So it's the y-axis. And so we can expect these values as we make these other x and y values, find other y values and x values. We're expecting the x values to get very, very, very close to 0. Okay, and this can be proven because the next y value I would choose is -2. So that'd be 10 to the power of -2 is x, which is 1 over 100. It's 1/100th, which is 0.01. So you see, that's already very, very close to 0. And it's just going to get closer to 0 if you were to find other values, but I don't really need them. And so for this, it cuts pretty quick, right? Here's what I mean by that. So this is that's getting really flat right there because it's going to the right very quickly. But then even right here, from my purple point to get to the red one, it's going to curve. Let's see if I can do a little bit better than that. Kind of like this here. So, again, is that perfect? It's not, but it's pretty good. Like, it shows an understanding that this blue line is never actually going, it shouldn't get to the y-axis, touch it, or cross it. It definitely doesn't cross it. Okay, so if you start putting in stuff like, it's going to go over here, no, that's you're going to lose lots of points on an exam or a quiz. So don't do that thing. Make it look nice, and by showing that you're curving it this way just helps us to understand that you know that it's going to just get really close to that y-axis there.